Have you ever, like, just stopped and thought about how a basketball falls? Like, it seems to just know how to fall, right?
Yeah.
That perfect sphere shape, it's like it dictates how it interacts with gravity, bounces back up in a predictable way.
Right.
That, my friend, is geometry at work.
It is.
And as we're going to discover in this deep dive, that's just like the tip of the iceberg when it comes to the universe. And today we're exploring the surprisingly deep connection between math, specifically geometry, and the force that keeps our feet on the ground, gravity.
Yeah.
And our guide for this journey, excerpts from the book The Gravity of Math by Steve Nadis, Shing-Tung and Mei-Heng Ye.
You might recognize Shing-Tung. He actually won the Fields Medal. Think of it like the Nobel Prize for Mathematics. And his journey to that incredible achievement is actually woven into this book, which I thought was really fascinating.
Right. Talk about an overachiever. He was already fascinated by Einstein and relativity, like as a high school student in Hong Kong. And even without like the advanced math that he clearly knows now, something about those ideas just like clicked with him, you know?
It speaks to the power of curiosity, wouldn't you say?
Yeah.
That early spark. It set him on this path to eventually exploring the very geometry of the universe, which is just, it's fascinating.
Okay, so let's rewind a bit, give a little context for people. We've all heard the story of Newton and the apple, right?
Right.
Classic Physics 101.
Yeah, it's almost cliche at this point, but that simple story, it sparked a revolution in how we understood gravity.
But here's the thing. Even Newton admitted he had no idea how gravity actually worked. He could calculate its effects.
Right.
But the underlying mechanism, total mystery.
That's where Einstein enters the picture.
Yeah.
He used these elegant thought experiments to just completely revolutionize our understanding of gravity.
Like, imagine you're unfortunate enough to fall off a roof. Do not try this at home, by the way.
Please don't.
But the point is, Einstein realized that while falling, you wouldn't actually feel your own weight. You'd be weightless because the acceleration of the fall is canceling out the feeling of gravity.
It's relative, right?
So our experience of gravity is totally dependent on our frame of reference.
Yeah.
That's wild.
Exactly, and that's the core of Einstein's equivalence principle. He demonstrated that acceleration and gravity are essentially two sides of the same coin.
That's mind-blowing.
It is.
Okay, but get this, Einstein actually considered math to be, and this is a, quote, superfluous learnedness at one point. Can you believe that?
Really? It seems ironic, doesn't it? Because
Right?
his pursuit of really understanding gravity, it forced him to embrace increasingly complex mathematics,
Right.
particularly non-Euclidean geometry.
Yeah.
He realized that he needed a whole new way to describe space itself,
Right.
one that could accommodate curvature to truly explain how gravity operates.
And that's where it gets really interesting, right? We're talking about redefining the very fabric of space.
Absolutely.
But before Einstein took on this challenge, there was another brilliant, albeit shy, mathematician who laid the groundwork. Bernhard Riemann.
Oh, Riemann. Such a classic example of someone whose work was so ahead of its time.
Right.
Like, picture this. You're asked to give a lecture, but on the one topic you feel least prepared for.
Oh, talk about academic stage fright. I can't even imagine.
Exactly. But faced with that exact situation, Riemann ended up giving this lecture that would revolutionize our understanding of space and ultimately pave the way for Einstein's breakthrough years later.
Okay, so what groundbreaking thing did Riemann do? I'm like ready to have my mind blown here.
Okay, so for centuries, mathematicians, they primarily focused on Euclidean geometry, the geometry of flat surfaces like a tabletop.
Right.
But Riemann, he asked this radical question: what if space itself is curved and not just the objects within it?
Hold on, I need an example. What's the difference between like a basketball being round in a flat room versus space itself being curved?
That's a great question. Okay. So imagine a flat piece of paper versus the surface of a globe.
Okay.
That's the difference between extrinsic and intrinsic geometry.
Got it.
The paper, it's inherently flat no matter how you bend it, right?
Right.
That's its intrinsic geometry.
Okay.
But the globe, it has an inherent curvature woven into its very essence.
Okay, I think I'm starting to grasp it.
Yeah.
So Riemann basically gifted us the mathematical language to describe curved space.
Yes.
Which Einstein then used to describe gravity.
You got it. It perfectly illustrates how seemingly abstract mathematical concepts can completely revolutionize our understanding of the universe. But Riemann's genius didn't stop there. He also introduced this powerful tool called the metric tensor.
The metric tensor. Okay, that sounds a little intimidating. What exactly is this metric tensor, and how does it relate to everything else we've been talking about?
It's like a mathematical ruler for this curved space-time we've been exploring. You see, in flat space, we use the Pythagorean theorem, a squared plus b squared equals c squared, to find the distance between 2 points.
Right, the classic.
But in the warped landscape of curved space-time, that old theorem, it doesn't quite cut it. The metric tensor swoops in to give us a more powerful tool to measure distances, accounting for that fact that space itself can be warped and bendy.
So it's like a more nuanced, flexible ruler that works even in the wonkiest parts of the universe.
Exactly. It helps us navigate this mind-bending terrain, you know.
Okay, I'm starting to see how it fits in. But how does the metric tensor connect back to gravity itself?
That's the truly fascinating part. The metric tensor, it actually defines the gravitational field. It tells us how space-time is curved at any given point, and that curvature, that's what we experience as gravity.
So wait, are you saying the metric tensor is basically the language of gravity itself?
Precisely. And it's a language full of these elegant connections. For example, general relativity, which describes gravity as we understand it today, it actually simplifies to special relativity when space-time is flat, meaning there's no gravity to warp things.
So special relativity is just a specific case of general relativity, like a subset of the bigger picture.
Exactly. It's quite elegant, wouldn't you say? The more general theory, it encompasses the simpler one, just like a set of those Russian nesting dolls.
Okay, that is undeniably cool. But what about those extreme cases where space-time gets incredibly warped? Those cosmic monsters, black holes.
Ah, black holes. The ultimate consequence of gravity going haywire. Even Einstein himself was initially skeptical about their existence. Did you know that?
He was. I thought he basically predicted them.
He did, through his theory of general relativity. But even Einstein found them a bit hard to swallow at first. He called them a true disaster, like some kind of cosmic wardrobe malfunction. It was actually Karl Schwarzschild, a German physicist stationed on the Russian front during World War I, who found the first solution to Einstein's equations that described a black hole.
He figured that out while serving in the trenches of World War I. Seriously.
It's a remarkable story. He used his downtime amidst all the chaos to work on these incredibly complex equations. And what he found, absolutely mind-boggling.
Okay, so what exactly did he find? What makes a black hole so, well, black hole-y?
Schwarzschild's solution predicted the existence of an event horizon. It's a boundary in space-time where gravity becomes so intense that absolutely nothing, not even light, can escape.
Okay, that's intense.
It is. And at the very heart of a black hole, Schwarzschild's solution predicted something even wilder. A singularity.
Singularity, what's that?
Imagine a point of infinite density and curvature, where the very laws of physics as we understand them completely break down. That's a singularity.
So a black hole is basically a cosmic glitch in the matrix, a place where our current understanding of the universe just stops working.
You could say that. It's a point where our current theories hit their limits.
Black holes are officially terrifying. But I have to ask, did anyone try to figure out what's actually going on inside a black hole? Beyond that event horizon.
Of course. That's where things get even more interesting. Inside a rotating black hole, and most black holes are thought to rotate, there's something called the Kachi horizon. Think of it like a second horizon, even deeper inside.
A second horizon, like a bonus level of cosmic weirdness.
Exactly. For a long time, physicists believed the Kachi horizon was another singularity, marking the absolute end of space-time. But then, in 2017, mathematicians Mihalis Fermos and Jonathan Look, they made a groundbreaking discovery.
What did they find?
They were able to prove that the Kachi horizon is actually a weak singularity.
Weak meaning it's not the end of the line.
Exactly. Their work showed that, theoretically, a particle could actually pass through the Kachi horizon.
Wow. So maybe black holes aren't quite as completely unforgiving as we thought. But hold on a second. Are all black holes the same? What about those spinning ones I've heard about?
Ah, those are called Kerr black holes, named after mathematician Roy Kerr, who discovered their solution in 1963. And trust me, they're even weirder than Schwarzschild black hole.
How so? They already sound pretty strange.
Well, Kerr black holes, they actually have 2 event horizons, not just one. And as if that wasn't wild enough, they also have something called the ergosphere. It's a region surrounding the black hole where space-time itself is dragged along with the black hole's rotation.
So it'd be like trying to swim upstream against a cosmic whirlpool.
Exactly. And if you were unfortunate enough to fall into a Kerr black hole, you wouldn't just be crushed by gravity, you'd be stretched and spun like cosmic spaghetti. Not a pleasant way to go.
Definitely not on my bucket list.
Yeah.
But before my brain melts down from too much black hole talk, can we switch gears for a bit? Maybe something a bit less intense?
Of course. What other mysteries of the universe would you like to unravel today?
Well, since we've been on this whole geometry kick, what about those extra dimensions I've heard whispered about in hushed, slightly terrified tones? Are those even real, or just something mathematicians made up to keep things interesting?
Extra dimensions.
Yeah.
It's not just science fiction, though it definitely sounds like it.
Right.
It's one of those concepts that just pushes the boundaries of what we think we know about the universe.
So it's not just mathematicians messing with us. There might be more to reality than we can see.
It's a real possibility, and one that's actually deeply intertwined with this quest to unify the fundamental forces of nature.
Okay.
You see, even after achieving the monumental feat of, formulating general relativity, Einstein wasn't content.
It's never enough for these physicists, is it? What more could he possibly have wanted?
He dreamed of finding a single, elegant theory that could explain all the fundamental forces. A true theory of everything.
Okay.
Gravity, electromagnetism, the strong and weak nuclear forces. He believed they were all connected somehow, just different expressions of one underlying principle.
That's a pretty ambitious goal, to put it mildly. So how did he go about tackling that?
That quest, it led him down some truly mind-bending paths, including something called Kaluza-Klein theory. Now, remember how we were talking about curved space-time?
Yeah.
Kaluza-Klein theory took that idea and ran with it, suggesting that there might be extra hidden dimensions curled up within the fabric of space-time itself.
Okay, hold on. We've already established that space-time is curved, and now you're telling me there might be extra dimensions hiding within those curves. It's like a cosmic game of hide and seek.
Exactly. Imagine a garden hose.
Okay.
From a distance, it looks like a one-dimensional line, right?
Right.
But zoom in closer, and you see it's actually a two-dimensional surface.
Okay.
An ant could walk along the hose, or it could walk around it. Kaluza-Klein theory suggested that our universe might be similar, with extra dimensions curled up so tightly that we can't perceive them directly, like the ant's circular path around the hose.
Okay, so these extra dimensions would be like tiny curled up dimensions that we just can't see because we're stuck in our four-dimensional world. I got it. But how does that connect back to unifying gravity with the other forces?
That's where things get really interesting.
Okay.
Kaluza-Klein theory proposed that electromagnetism, the force responsible for everything from electricity to magnetism to light itself, is actually just a manifestation of gravity operating in these extra hidden dimensions. It's like saying that gravity and electromagnetism are just two sides of the same coin, but we can only see one side because of our limited perspective.
Whoa. So it's like those optical illusions where you see one image, but if you shift your perspective, a whole other image pops out.
That's a great analogy. We're only seeing a slice of the full picture.
Incredible. So did Kaluza-Klein theory turn out to be the answer to unifying the forces?
It was a brilliant idea. However, it did run into some roadblocks.
Such as?
For one, it predicted the existence of particles that have never been observed. But the idea of extra dimensions, that didn't go away. In fact, it experienced a resurgence with the advent of string theory.
String theory, the one where everything is made of tiny vibrating strings.
That's the one. And string theory relies heavily on geometry, specifically on these incredibly complex six-dimensional shapes called Calabi-Yau manifolds, which are thought to be curled up in those extra dimensions.
6 dimensions? Those sound pretty intimidating even for this show. What exactly are Calabi-Yau manifolds, and what do they have to do with string theory?
Imagine them as the geometric scaffolding for string theory, like the blueprints for how the universe is put together at its most fundamental level.
Okay.
They determine the properties of particles and forces within the framework of string theory.
So the shape of these manifolds dictates what kind of particles can exist and how they interact with each other.
Exactly. It's like saying that the geometry of these hidden dimensions shapes the very laws of physics in our universe.
It's an incredibly elegant and mind-blowing concept, I have to say.
It really is.
But has string theory actually been able to prove any of this? Or is it all just really, really compelling math?
It's a fair question. String theory is still a work in progress, and it's incredibly challenging to test experimentally.
Right.
but it has provided some remarkable insights, like explaining the entropy of black holes, for instance.
Entropy, that's like a measure of disorder, right?
Exactly. And black holes are incredibly mysterious objects with surprisingly high entropy, meaning they possess a tremendous amount of internal complexity. String theory has actually been able to shed light on where that complexity comes from.
Okay, so even if string theory hasn't quite given us the ultimate theory of everything yet, it's still been an incredibly fruitful area of exploration.
Absolutely. It's a perfect example of how the interplay between mathematics and physics can lead to groundbreaking discoveries and deepen our understanding of the universe.
You know, we've covered so much ground today.
We really have.
From falling apples to the event horizons of black holes. From the quest for unification to the surprisingly elusive nature of mass. It's incredible to think that geometry, something we often think of as static and unchanging, plays such a central role in our understanding of this dynamic, ever-evolving universe.
It's a testament to the power of mathematics as a language, wouldn't you say? It allows us to describe and explore these realms that are so far beyond our everyday experience, from the unimaginably small to the incomprehensibly vast.
Absolutely. And for those of you listening, keep questioning, keep exploring, and never ever underestimate the power of curiosity to unlock the secrets of the cosmos. We'll catch you next time on The Deep Dive.